Hello, everyone. So we are very happy to welcome you live from Paris, a little flooded Paris, but we're on the fourth floor, so we're safe. And it's always a special moment to answer your question live. So we are here with George, and we'll try to answer the questions of the first 4 weeks. I'm sure you'll have, and we have seen questions about, future courses, future weeks. Remember that next week we are studying black holes and the week after gravitational waves. So we'll reserve these questions for the next Hangout, which will be on the final week. So this week we focus on the content of the first 4 weeks, and especially the last 2 weeks, the one on CMB, which was, if you want, George's week, and the one on dark matter and dark energy. We have received many questions on the website, through Twitter, through this Google Hangout. So we'll try to address some of them. And for those that we have not answered, well, then we try to answer them in a written form. Okay, so hello again. And hi, George.
Hello.
And so let us start with a question which was sent by Alvaro, and which is of a philosophical nature. We'll come back to more precise questions, but I thought we might start with this one. So Alvaro says we are asked to believe in theories of the beginning of time and space with indirect proof, or even worse, with proof that we are still looking for. Isn't in this science behaving as religion? Okay, so why don't
All right.
you answer this one, George?
I think there's three different parts that you might answer this. First of all, when we talk about science, we talk about approaching things with a certain methodology and with a certain worldview. And that worldview is that the world is simple and understandable and obeys rules and it's logical and eventually self consistent. And so we then approach various things. And it's true that when we approach talking about the beginning of the universe, we take a lot for granted. If we look back, we're celebrating this year 100th years of general relativity. If you look back to the early days of general relativity and our understanding of cosmology was very weak. There was very little evidence, but we thought general relativity was a good approach, and we thought we could study it and do the mathematical equations and make observations and understand. And the progress that we have made has been really very tremendous. We have, particularly in the last 25 years, because of new technologies and because of new observations and computer abilities, been able to test our models of cosmology and be able to test the observations that we can be very confident about the results we have because they stand up to the scrutiny, that is the comparison of actual observations with consistent predictions from the theory itself. So when we say we believe it, the answer is a little more complicated than just believing. What we say is we take this as our model, we compare it to observations. If it disagrees with the observations, then we must modify the model or replace it with a new model. That's what we did with gravity. We went from Newtonian physics, which was our model for 200 years, to general relativity, which has been our model for 100 years. Both of them have their ranges where they're valid. We keep testing general relativity to see if it's also true, but we use it as our accurate model.
Yes, and maybe I should add, so in this course, we're dealing with two types of questions. Uh, and those are scientific questions. There are the questions that led to some predictions which have been observed, or we are talking mostly of observation. Um, and so questions that lead to predictions that have been checked in the sky. And then there are questions where we don't yet have the answers, but there are scientific questions in the sense that we hope that in the future they will lead to some predictions that can be tested. We have sort of refrained from going to more adventurous questions. There's topics that I like extra dimension of space-time, wormholes, Okay, we did not touch that because we thought those were speculations which are a little too wild. We try to focus on questions that we are asking ourselves. Some questions that have been solved, and some questions are still, waiting for a solution. But we're trying to focus on the mainstream questions at this point.
So when we do this, we present the stuff the way you get in the textbook often. Those are very well established theories that have been tested against observations. We give you the part where we think the tests have been very good, or the things that are necessary to give a complete picture. And what you'll see in some of your questions that we see are things we don't know the answer to yet, but we have expectations of what should happen, and we'll be surprised if they don't. But that's how you make progress in science.
And you'll see in the last week, actually, with the discovery of gravitational waves, that these, both these, some of the questions that we raise, might seem a little wild, but it's even more surprising that they get very precise answers, from observations. But we'll come back to that in the last week. Okay, so let's start more detailed questions. And of course, there's few concepts which are difficult to digest, and one of them is the concept of the infinite universe. So let me pick up some questions. For example, the first one from Julie. If the universe is infinite, that's a question on Twitter. If the universe is infinite, how can it be expanding? Surely something that is endless cannot get any bigger.
Right. Well, it would seem that way until you just don't worry about it. You just say, all right, imagine the universe, we only think about two dimensions, this great huge sheet. And on the sheet, I put a bunch of lines, make out a regular grid, and then I just stretch the sheet. And so, it becomes twice as big, the lines are twice as far apart, but that goes on to infinity. So in that case, I don't have a problem with expanding it, and I can imagine it in 3 dimensions. And even if I had more dimensions, I could suppose that would happen. But we concern ourselves with 3 dimensions. So the answer is, the trickiness about infinity is that infinity and 3 times infinity or 5 times infinity they're all infinity. And so you have to be careful when you start saying, how can it not expand?
Yes, and so there's another question on the Hangout by David on the same theme, and I think that's okay. He's asking us. Okay, he comments that it seems to be a really fundamental. Okay, I just selected it. It seems to be a really fundamental question as to whether the universe is finite or infinite. There seem to be differing opinions about this among cosmologists. Can you tell the arguments for and against the idea of a finite universe? So maybe I take this one. As I think we explained in the course, we are observing the sky. We're observing the universe, or at least that part of the universe that is accessible to us. And according to Einstein's theory, Einstein tells us, or Einstein's theory, Einstein's equations, when you solve them, tell us that the universe is finite or infinite depending on the amount of energy per unit volume available in the universe. So of course, we don't know the universe as a whole. We just know our observable part, but we can compute the amount of energy in this observable part. And we find out that this corresponds, that's 10 to the minus 26 kilogram per cubic meter, that corresponds to what we know as a flat space. And I think, as we have insisted in the course, flat space just means a space which is like Euclidean space, a space where the geometry is standard geometry. Now, in this case, the universe is infinite. Flat space has to be infinite. It has got no boundaries. Now, of course, this value exact, if it was a little higher, a little more than 10 to the minus 26 kilogram per cubic meters, then the space would be closed and it would be finite. If it's a little smaller, then the space would still be infinite. So we are just on the sort of limit value. And some people might say that maybe there's a little chance that we are just above that value, and so the universe will be closed and it will be finite. I think most people in the community, and I'll let George comment on that, but most people in the community think that this is not a sort of, by chance that we are exactly at this value. There is most probably a profound reason for it, and that the universe indeed, in its largest dimensions, is flat. And the profound reason is the theory of inflation that we have studied during the course.
So I think there's no real clear agreement among all cosmologists whether the universe is infinite or finite. And in fact, there's even a small set of people who've considered universes that might be flat, but were finite in size, the same way in the early days of Pong and there's a rocket game where the rocket would go off one side of the screen and reappear on the other side. That you could take a finite cell and identify the edges. So this edge would be identified with that edge, so that when the rocket went across there, it would come back on the side. We can tell by looking out in space that the scale size of that cell is extremely large, is at least approaching the size of the universe we can see today. So it is conceivable, both when you start talking about the geometry, that's what Pierre was talking about, that the geometry is set by the energy density per unit volume and the energy per unit volume. But there's also a topology, which is, do you identify edges? Do you make it like a torus or something else? And those are things we can try experimental tests of. And so far, the universe has proven to be large. We can't prove that it's infinite or finite. And people have different reasons, different theoretical reasons for wanting it to be either case or the dividing case. Inflation does drive it, and the accelerating universe drives towards a flat universe. Just, you can imagine a sphere, you make it bigger and bigger, it gets flatter and flatter. So in the case of the early universe, if we have inflation, it makes the universe very flat.
So there's another question from Alexandre, which is, again on the same theme. Um, basically, is asking us, because we only see a finite part of the universe, and this is in this finite part of the universe, what we call the observable universe, that we compute this 10 to the minus 26 kilogram per cubic meter. So how do we know that, this is the case in the whole universe? And of course, okay, the answer is that we don't know. We have to make assumptions. And so we make a big assumption, which is that we are not in a specific part of the universe. So that means that at least, when we look at the larger scales, then we assume that what we see is what someone else who would be another part of the universe would see. So this is sometimes called the cosmological principle, which is that, precisely stating this, that we are not in any specific part of the universe. And so the observable universe that is within our reach is very similar to the observable universe that another observer very far away outside our observable universe. It's exactly, it has got similar properties than what this observer would see in the sky. So, but that's an assumption, and so clearly we have to state some of these assumptions. Any comment on this? No. Okay, so let's move to CMB, cosmic microwave background, and so let me pick up a question from David. A question about the quantum fluctuations. Okay, so let me select this question. Okay, did the quantum fluctuations that resulted in CMB temperature variations occur during the early stages of a Big Bang, or did they cause it?
Okay, so we're not absolutely sure what caused the Big Bang. We're approaching this model we call inflation, but we have other observations. We know that these happen very early in the universe. They could be a result of this epoch called inflation. We don't know if there was something that went before inflation or we directly came into an inflationary period. But we have this rapid expansion of the universe, accelerating expansion of the universe early on in our model. And we have continued expansion after that, although slowing for that time period until more recently. And we can tell something about when these fluctuations appeared, and we can tell they appeared very early. The reason being they show up in a particular pattern, which is caused basically by them being put in very early and then be allowed to develop over that early time period, the 400,000, first 400,000 years, to appear. Now, whether they appeared at 1 second or, one, you know, 10 to the 30th, 10 to the minus 30th of a second, that is, a nanosecond or whatever it is. We can't tell for sure about that, but we think that's the most logical time for them to have appeared. And for quantum fluctuations, the earlier the better, because that's when quantum mechanics is more and more important. And when we make our model, our mathematical models, we can predict what the fluctuations should look like. We can predict how they should evolve, or we should see them in the cosmic microwave background. And we see those patterns very precisely. And so that's something that tells us, yes, they all sort of appeared early, they all appeared roughly the same time, and then they've evolved since then, and they have the pattern that comes from that. So we're very much confident that's what's going on, and that we understand them very well, because we can predict a lot of their behavior, not only their amplitude, but the way they're moving around, and so forth.
Thank you. Okay, let's have a couple of questions about expansion. Okay, maybe one, we had several questions about detection. For example, one from David. What are the perceived implications of a much greater rate of expansion now detected by Hubble? George.
So this is, there is a paper that was brought out last week and made public and appeared in the news the last couple of days, claiming that people have measured the rate of expansion of the universe locally. That is, they've been using the Hubble Space Telescope to look relatively close by us. Up until this point, our measurements of the Planck satellite, which measure across very great distances in the universe, have been the most precise measurement of the expansion rate. And those two expansion rates just disagree with each other by about 5%. And the local one seems to be expanding faster. And the question is, did these new measurements really improve their errors to where they're down to 2.4% to compare to the Planck's 1%? And is there some reason the local expansion rate should be different than the global expansion rate or the historical expansion rate? And so the authors of the paper go in great detail and explain what all they've done, and they've done a lot of things to make the measurements much better than the previous measurements. And there's still limited statistics because they only get a couple of supernovas per year getting added on. And but their measurements are definitely an improvement over where they were a few years ago. And it adds it up. And they even say, all right, well, we expect the two sets of measurements to agree. What could cause them to disagree? And they make a list of potential things, one of which is if there's an extra species of neutrino, or effectively half extra species. We don't know. We always will be looking for these kind of things. It doesn't seem so likely. It seems to me it's likely that there's something else going on. Some years ago, people used to speculate that perhaps the accelerating universe wasn't really accelerating, just that we were in a local bubble that was expanding more than the area around it. I think that most people have given up on that idea, but this is a kind of a direct test of that, and we'll see how it goes. This is brand new science. It has to be reviewed by the other people in the field, and we have to see new data coming in. But it's encouraging to see the errors getting smaller, so that we have this what we call tension between the two sets of observation. Will it reveal something new, or will we find out that some small mistakes were made, and they will eventually come together?
But that doesn't change the general picture that the universe is, is undergoing some acceleration of the expansion. Uh, okay. Now, okay, one question about light. So where did I get this question? Okay, there was a question. I don't find it anymore. Okay, yes, from Ian. And the question was, if light has no mass, how is it affected by gravity? So indeed, you're right. Light has no mass. So to be precise, photons, which are the constituents of light, the particles that are the constituents of light, are massless, and they have no mass in the in the classical sense, but also when there is gravity. So, but they follow the shortest path, and so that's why they are subject to gravity. They are not attracted, by gravity itself in a sense. You should by now realize that there are many manifestations of gravity. So manifestation of gravity that we're used to is the attraction between two masses. But there are other effects of gravity, and one of them is the distortion of space-time. And so if photons are subject to gravity, it's not because they have a mass, it's because they follow the shortest path in space-time. And when space-time is curved, then the shortest path is no longer a straight line. So this is a reason. But that's a different manifestation of gravity than what we see usually, which is the attraction of two masses.
So I'll add to that because this was always a question, even before general relativity was fully done, which was, would light be attracted by massive gravitational? And in fact, the first prediction that there would be something like black holes came before general relativity existed, that there might be enough attraction to do it. And the reason is, when Newton wrote his laws, the most dense amount of energy we had was mass energy, the mass times c squared. Things that are moving, their kinetic energy is much smaller, but a photon doesn't have a mass, it just has its kinetic energy. And so people realized that if they thought about, thought experiments, that light would be attracted by gravity, and there would be this bending of light. It turns out to be a factor 2 less than general relativity gives, because general relativity bends both space and time, and that extra factor from the time gives you another factor of 2. And so there were predictions, and in fact, between the time general relativity was first written down in 1915 until 1919, when the eclipse was measured, there was a refinement of the calculations, and it was shown that general relativity predicted this extra factor of 2, and that was why the eclipse tests were considered so important. They were comparing Newtonian gravity to Einstein gravity to other alternatives. And so the fact that it came out to be closest to general relativity made Einstein a worldwide celebrity overnight.
Thanks. So I'm being told that the sound is, by some of you, that the sound is pretty bad. So please send us some comments if really the sound is bad, or if it's just, one or two of you. But if the sound is bad for everyone, then we should try to solve the problem. At this point, we have no problem on our end. So please send us comments if you still have problems hearing us. Okay, so let me come to a question on the Hangout. Let me select this. This is from Michael. And Michael says that we say that we need dark energy to be a component of inflation to form a flat universe. And yet, its effect on the acceleration of the expansion did not start until quite late. So why is this? My impression is that there is a confusion between dark energy and vacuum energy. We tend, as Michael points out, to call dark energy the component that is responsible for the recent acceleration of the expansion of the universe. And we call it dark energy because we do not know exactly, what is this form of energy, but that's indeed associated with the late acceleration of the universe. Now, there was a very early acceleration of the expansion of the universe, which is what we call the inflation phase. And so that's different. That one was very early. And one might actually, a question that we are asking ourselves is, why is it that the expansion of the universe accelerated at the beginning of the history of the universe and very recently? That's an open question. Now, we believe that vacuum energy, which is the energy of a vacuum, was responsible for the first period, the period of inflation. And so, a possibility, and I think at this point, according to observations, rather convincing possibility, is that the same vacuum energy is also responsible for the late acceleration of the expansion of the universe. And so you see, in this case, we would have to understand, why it was, very early and then very late that the vacuum energy was, if you want, the driving force of the expansion of the universe.
And one of the big questions is, why is the energy scale so different? Right? We're talking about a tremendously high energy scale in the early universe and a very, very low energy scale at the present day. And if it's the same thing, how could it make that transition? Or is it a different manifestation of a similar kind of force? And so we don't know. That's part of why we're doing science. It's one of the exciting things we're doing. And now there are many experiments and observations proposed to try and look and understand what's going on.
Okay, let me pause for a second to check whether we have solved this sound problem or not. Yeah.
Il faut fermer les trucs, je l'ai expérimenté, il faut fermer simplement il faut qu'ils ferment leur mail et tout ça, qu'ils aient juste YouTube d'ouvert sur leur ordinateur.
Et si tu as juste YouTube, tu n'as plus de problème.
Okay, so I'm being told that some problem arise if you have several things open. For example, Google Hangout, Google Plus, and at the same time YouTube. So the best is just to listen to us on YouTube, for example. Okay. Now we had another question. Yeah, an interesting question from Michel. Again, about the acceleration of the expansion of the universe. Michel is thinking about, as two questions, but that have to do with acceleration. Over time, does this acceleration of the expansion vary, which means that there are different rates of acceleration? Okay, maybe that's the first question. We sort of answered, this one, because we said that indeed there was a huge acceleration at the very early times. Then it stopped. That didn't mean that the university was not the universe was not accelerating, but it was still accelerating, but no longer. I'm sorry, the universe was still expanding, but no longer with an acceleration. And that's a time, the periods that we call dominated by radiation or dominated by matter. And then more recently, there has been again an acceleration. So indeed, the acceleration has been varying with time over the history of the universe. Now, the other question is interesting. I'm sorry.
Yeah. Let me add a little bit there. So this is one of the detailed questions we ask in cosmology, and Pierre knows this, but he wasn't thinking about it. When we talk about inflation, the early, very high energy one, we think it's slowly losing energy, and therefore the quantum fluctuations get to be a little smaller as time goes on. And we measure what the amplitude of fluctuations are on the very largest scale, the next largest scale down to the smallest scale we can see. And we see a very slight tilt, which tells us we think that the rate at which the universe is accelerating, the very early universe, is very slowly slowing down. And we have a prediction on what that is, and our measurements seem to agree with that. It's a very tiny tilt, and we're barely able to manage, but we're measuring it. So we see this very slowing down, and then we think inflation ends, and then much later on, the dark energy causes the universe to start accelerating again. If it's a vacuum energy, a fixed vacuum energy, it will not change with time. If it's something else, it will. Here in the more recent times, we have much poorer limits on how it might be changing with time, but it's not changing by more than 10% over the last 5 billion years.
And so the other question of Michel is the following. That's, whether acceleration is is changing across the universe. So is the acceleration of expansion uniform across the entire universe, or does it have higher rates of acceleration in pockets of the galaxy? So that means maybe more dark energy in some places and less in some others.
So this is a question where the first order of the answer is it's uniform across the whole universe, not just our galaxy. But if it really is not a vacuum energy, but it is some new substance, there could be the equivalent of sound waves in this new substance. And that means in quantum mechanical fluctuations, there could be very small variations. We expect those to dissipate out at the speed of sound, which should be near the speed of light. And so the answer is we think it's very uniform, but we have to do observations to make sure that's the case. So far, it looks fairly uniform.
But indeed, that's a sort of topic of study. There's some models where people think it might be not completely uniform. And of course, in this case, the picture would be slightly different. But as George says, at this point, we don't see any, at least in the pocket where we are, the observable universe, we don't see any variation of the expansion. But as we get to know more and more and also observe deeper and deeper, we might have surprises. So let's stay tuned on that in a sense.
So we kind of make a distinction between the expansion of space and the expansion of some of the contents, like the dark matter and the ordinary matter. We think that expands for a while, but the local overdensities collapse back down to form the galaxies, the clusters of galaxies. So you're right in the sense that a galaxy is a variation, but we think the space itself is still expanding very uniformly.
A very interesting questions from Steve. How does time fit into the Big Bang theory? Did time also expand from nothing at the Big Bang, or did time exist before it? If so, what was happening prior to the Big Bang and for how long? Okay, let me say we have no ideas. Well, we have ideas about that, but we certainly have no definite answers. Okay, maybe I should say that indeed, we have been insisting in the first course that space and time are related, and so there's some time effects when you look at different points in space. There are some space effects when you're looking at different times in the evolution. So it seems that space-time is the the general concept. On the other hand, when we are looking at the universe, there's this expansion, and somehow time has a special role, precisely because of the expansion of the universe. Okay, we had some problem with lights here, but no, that's
No
okay.
flood.
I
No
think
flood, just the lights.
this is fine. Light went out, but no, that's okay. Okay, you still see us. It's not yet dark. Okay, where was I? Yeah, that's what it takes. When you start answering questions about about the status of time, suddenly light blows out. Okay, never mind. So I was just explaining that indeed, the expansion of the universe makes time play very okay. So
Go ahead and answer.
okay. I have difficulty concentrating because that's there's motion in the room. So nobody wants me to answer questions about time, it seems. Anyway,
I'll give an answer for a while. So there are people who try different approaches, and there's a whole set, including Hawking and Hartle did a model of the universe where the universe pops from nothing end to an existing time. So there's an actual beginning of time, although a funny kind of beginning of time. And when I say nothing, I don't mean empty space. I mean nothing, literally nothing. You create the universe, and you make time and space begin. You make it begin, but you can make it begin like it was a sphere. So there's no any places equivalent beginning or ending. And in that case, the universe will go on for a long time, and then eventually it will collapse and go back to nothing. But there are other models like Linde's eternal inflation, where the universe is mostly undergoing this inflation, and there are quantum mechanical fluctuations in small pieces, but off to be normal spacetimes like our own part of the universe. And we don't know the answer yet. We hope there's going to be telltale relics and pieces of evidence that allows us to distinguish these. If not, just understanding the laws of physics better will help us approach that. So there is a symmetry between space and time, and it even can come to the creation of space and the creation of time. In some models, that's just very straightforward, but in almost all of them, it's practically that shape.
Yes, let me take the opportunity to answer a question which quite often is raised and has been raised over the last weeks, which is what happened before the Big Bang. My usual answer is that that question might be not the right question to ask, because we tend to think, and those are speculations at this point. This is not proven, but those are speculations. We start to think that the very notion of space and time might not make sense very close to the Big Bang. And I quite often give an image to let you understand this. If you look at this table, which is just in front of us, for a long time, people were thinking that this was made of wood, continuous matter. And it's only in the early 20th century that what we realized that actually this was absolutely discontinuous. And if one looks very closely at it, it's made of atoms. It has got a non-continuous structure. It's broken into very elementary pieces, which are the atoms, and it's mostly empty. Now, we tend to think that very close to the Big Bang, it might be similar in the sense that in this room, for example, time and space appear to be continuous. But maybe if one was looking at, and I don't know how to look at that, but if one was looking at very short time and durations and very tiny pieces of space, one would realize, and that maybe that's what happens in the case of very close to a Big Bang, that time and space are discontinuous. If you want, they are made with grains of time and grains of space. We don't know exactly what these grains would be, and there are some theories. People are trying to get this, and so the notion of continuous space and continuous time would be sort of what we observe, but our senses sometimes are betraying us. So it's the notion, the continuous space and time would be, we say, emergent notions at the time of the Big Bang. And so you see that if this picture is true, there are theories about that, but no, we have, this is a big open question. If this theory is true, or if this hypothesis is true, then maybe the question of what happened before the Big Bang does not make sense, because we would have to rephrase it in terms of these grains of space and time. So it's just, I know I'm just opening questions, but just to let you know what people are sort of thinking nowadays about what could happen at the Big Bang. Okay, so that was a long parenthesis on the Big Bang and on time. Okay, let me get other questions. I'd identified a few on the Google Hangout. Where are they? Just a second. Okay, that's a question for George. Okay, he didn't prepare the answer, I can tell you. Can you imagine a way to use vacuum energy for propulsion?
Okay, So when dark energy was the accelerating universe was first discovered, there were lots of people saying the Department of Energy in the United States or some of the agencies in Europe should be figuring a way to tack into the vacuum energy of space in order to provide power. And when you do the numbers, the amount of energy in a cubic meter is not very much. And so if you want to use it for anything, you have to think about using extremely large volume of space, sort of solar system size kind of quantities, or at least Earth orbit size quantities. And then it's a significant amount of energy, and you could think that maybe you could do something with it, but that's a tremendous scale to be making any tapping into the energy or anything like that. Now, can we use it for propulsion? I I don't think so. It's propelling the universe, causing the universe to expand faster and faster. Can we make it do that to a ship or to a spaceship, even in particular, right? And or an airplane, but a spaceship is what we'd have in mind. And the answer is, it's probably too small of energy to be useful. It's too small of energy density to be useful for that on a small scale. That in fact, the light coming from the sun, the solar cells are more powerful. However, if you understand the physics, you may be able to understand how can you create a kind of energy density that's like the dark energy that would allow you to locally create some propulsion. And so there are people who try to look at warping space-time or creating a particular kind of energy density that would be repulsive, that could kind of drive us away from its source. It looks to me like that's a very long way away before anybody has any serious ideas about that.
Okay, a question for me from Fawad. Pierre, you said that gravity is the engine of the universe. It's also causing the evolution of the universe. Can you please explain this? Okay, so there are two reasons why I'm saying that gravity is the engine of the universe. The first one is that we know that the full dynamics of the universe in its largest dimensions is governed by the laws of gravity, and the laws of gravity are Einstein's equations. So in that sense, for example, Einstein's equations, when you solve them, we didn't solve them in the course because that required mathematics, but you can believe me, if we solve them, then we find out, if we solve them for a universe, that is not static, but expanding or contracting, then we find out that every form of energy is contributing to expansion of the universe. So it's in this sense that I'm saying that gravity is the engine of the universe. So that means that, in a way, we saw in the first course that a mass is curving space-time, but this is more general than that. It's any form of energy has some influence on space and on time, and that's what what Einstein's equations are telling us. Any form of energy, not just mass energy. So this is why in the sequence we have been talking about, for example, vacuum energy. We have been talking about other forms of energy possibly than just the energy which is in the mass of material objects. Okay, so that's the first answer. The second answer is that when you think of it, of all fundamental forces, gravity is the only one that extends over extremely large distances. The microscopic forces, the forces that are acting inside the atom, the ones which are studied in high energy colliders, for example, have no effect at large distances. Now, the electromagnetic force should have an effect at very large distances, and this is related to the fact that the photon is massless. If the messenger is massless, then the range on which the force is acting is in principle infinite. But it turns out that the electromagnetic force is screened by charges. You have positive charges in the universe, negative charges, everywhere. And if there is a charge, for example, on this table, it might affect us. But very soon the charges in the wall and all this of this room will screen the effect of this charge, and so in principle this charge would have an effect on the whole universe because it sends out photons that could travel for a very long time. But in practice, it has very little effect at very large distances. And so we are remaining with a single force that is acting on extremely large distances, and that force is a gravitational force. And somehow this was known since the days of Newton, but we are just expressing the same fact, and now we're expressing it using Einstein's equations.
And you know it from your own experience. You stick to the Earth even when you shuffle your feet on a cold winter day and get a static charge. You don't get a very much static charge because the electrical forces are so strong, they pull the charges back and cancel. So you stay stuck to the Earth because of gravity, not because of electric charges.
Okay. A question about dark matter and dark energy. Can dark matter and dark energy be likened to a cosmic sea that we just cannot perceive as yet with our limited vision?
Well, certainly the dark energy we really think of as being like the sea, and that we think the dark energy is spread uniformly throughout, or very either almost completely uniform or completely uniformly all throughout space, and that it doesn't interact with light uh, in any sense. It would curve space-time, but it doesn't curve space-time so noticeably. And so, except for having the trajectories be straighter than they would otherwise be, we don't see any indication of the dark energy, except that the galaxies are moving apart faster and faster. The dark matter does kind of clump up some. We think it does not interact directly with light through electromagnetic force, but only through gravitational force. And there we see it because we can see gravitational lensing caused by the dark matter bending the space around it, and then the photons following those curved paths around clusters of galaxies where there's a lot of more dark matter than ordinary matter. So we think we see it, but we see it indirectly, the same way you see the invisible man by his footprints.
Thank you. A question, previous question was from Antosa. Now, a question which has to do with inflation from the Google Hangout. Assuming that the universe before the inflation phase was uniform, could not the properties of a CMB we see today have been created locally? Why does there need to be communication between all the areas of the early universe?
Okay, let me see if I understand it. So the question is, if you made if you make the universe, why do you have to make sure that it's uniform in some local sort of sense, or made some other way? And the answer is, when people, before we had inflation, people used to have to put in by hand the universe was the same everywhere. And the reason for that is very simple. If you look at where we understand the beginning of time to be, roughly 14 billion years ago, and you wait only 0.4 billion years, that's how long light travels from the beginning of the universe out to be a spot that we can see at the surface of the last scattering, where this cosmic background comes from. And we look at that, we can look and see how big that spot should be, and that spot should be on the order of 1 or 2 degrees on the sky, and yet we have 42,000 square degrees on the sky. That is, if we look at two things that are this far apart, they were not in causal contact since the beginning of the universe. So unless they were made to be the same at the beginning of the universe, then there's no reason they should be the same now. But we observe they would be the same to a part in 100,000 everywhere we look. So how do we explain that? Well, inflation is one of the ways it explains that. If we take a very small part of the universe, which was in good causal contact, got the thermal equilibrium, was all then therefore the same amount of photons everywhere, and you take that small place and expand it up to be very large, then when we look out, we see exactly the same stuff. And so what we really did is put a bunch of time in before to make things feel the same by having inflation. That is, we make the universe expand so much that even though it looks like it's a short time, it's expanded so much that it's become much bigger than what we can see, even though it was very small in causal contact earlier. And so inflation solves that problem for us. Otherwise, we have to just put in by hand. We have to declare, well, somehow when the universe started, it had to be in a condition of being completely uniform.
Yeah, to sort of complement the answer, let me make things even more dramatic. Uh, you know, remember, okay, we suppose the universe is infinite, but it would be the same thing if the universe was finite, but was not just restricted to our observable patch. And if, there are different parts of the universe that never talk to each other, that means that, there are other parts of the universe that might, be outside the observation. Now, if I look, for example, in this direction of the sky, this direction of the sky, if I, look at 14 billion light years from here, I see the Big Bang. Now, if I look in this direction, and I again look at 40 billion light years from here, I should see the Big Bang. Well, I don't see it because it's opaque and I've used light, but in principle, I could see the Big Bang. Now, why, if those two parts of the skies were never in contact, causal contact with one another, why is it that it's exactly, the Big Bang in this direction happened exactly, at the same time as the Big Bang in the other direction? So this is the type of, question that we have to ask, and we have to provide an answer. And in this case, the answer is precisely inflation. Otherwise, there is no reason that, two parts of the universe that never talk to each other would have exactly the same history, and, for example, would have exactly the same age. Okay, other questions? Let me see what I selected. Okay, I like when, okay, that's, yeah, when someone says, I don't think my question is a very good one. Usually those are, one can find some interesting aspects. So that's from Bell. And the question is, could the accelerated expansion of the universe make the same thing happen now or in the future? So I guess that means, could the same thing happen twice? Should I take this one?
Yeah.
Yes.
If you understand the question, I'm not sure. I
Yeah, no,
understand
I'm
it.
not sure I understand it. Okay, let's talk about events that because that's related to causality. Events that are repeated. Usually, it's in a closed universe or in finite universes that you're in danger of having this type of things, because then you might as the universe is expanding and then contracting. I think was a question. In this case, there would be a big crunch, and maybe the universe would start again in a Big Bang. So if the universe starts in a Big Bang, expands towards a maximum size, and then goes back into what we call a big crunch, and then it's periodic. So it keeps doing this. Okay, in this case, you could. Well, in this particular case, I don't think there's a problem with causality, but you could have universes when you have problem of causality, but usually we don't. We are afraid of space times where you can meet your grandmother as a child. That's not what we see in our universe today. maybe I should say something which has to do again with a connection between classical physics or gravity and quantum physics. Quite often one says that I could maybe I could get back to in some universes I could get back to a point where which is in my past, but probably because of quantum physics, which is not part of the gravity theory, but quantum physics is introducing some fluctuations, as we have seen, some fuzziness, and so you will not exactly get back to the same point, same event, and so you might be slightly close to it, but slightly away from it, and so in this case, you would not encounter yourself in the past, you would encounter some different there might be no such bridge into the past just because of quantum physics. Maybe we'll come back to that in future when we discuss more about the connection between the classical physics, classical theory of Einstein, and quantum physics.
So one thing that we can say is the universe looks right now to be very well ordered, very well structured, and very large, so that we can expect the time scale that the universe will be around before anything happens is quite some time. We're talking 100 billion years. However, if the universe keeps accelerating and fleeing, as you said, fleeing from the observer, then the universe gets more lonesome, because as the universe is accelerating, because it's expanding faster and faster, the galaxies which are in view, eventually they start going out of the view. They start disappearing because the space between the galaxies grows so much that light doesn't have time to travel across it before a new space is created. So that light never quite makes it to you anymore. They disappear from view. And eventually we'll be in the situation where it's only our local group of galaxies that's hanging out together. And before that happens, Fornax and Andromeda will merge, and then we'll merge with Andromeda, and we'll be just one galaxy in the otherwise empty-looking universe. So that could be pretty lonesome. But the timescales are very large compared to the timescales of civilizations or human lives or anything else. And so nothing seems like it's going to happen right away.
Okay, so I see that time is running. We've almost reached an hour. So let me take a last question from Graham. And the question is, and I'll first ask George to answer this one. I've prepared my answer. What is the one breakthrough in astronomical research that you like to see in the next decade?
The one, I have several I would like to see. I would like for us to really make progress on understanding gravity, and that's in a lot of ways. That is, with the discovery of gravity waves, then we want to have gravity wave astronomy. I would like us to understand gamma ray bursts, which we think are black holes that are making relativistic jets that are beaming towards us. There's a lot of places where we can start probing gravity in ranges where we might see something different, because we're all wondering how will we ever consolidate general relativity and quantum mechanics. What will be the resolution to what apparently is a conflict and the way those two pieces of physics work, and a breakthrough that leads us to understand those better, or some of the ones that I think would be most valuable.
Well, my own answer is that what is the one breakthrough I was expecting? Well, it has already passed. This was a discovery of gravitational waves. I was expecting it for in a couple of years, but it happened even more quickly than I expected. But certainly, I'm now looking forward to what it will be used for. I mean, all the exploration of the gravitational universe, that this will allow. We'll see that more in this coming week when we discuss black holes, and especially the week after. But stay tuned, because there might be some, look at your newspapers already this coming week. We expect a few announcements on gravitational waves. So, and I'm sure we'll be discussing these in the remaining 2 weeks. So that was my hope, that we would be discovering gravitational waves, and that was actually one of the reasons to organize this whole course, because we were thinking that this might be a real historical event. This is happening in a sense as we are discussing, and so we'll see much more of that in the next coming weeks and in the next 2 weeks for this course. Okay, well, thank you, George.
Thank you, Pierre.
Okay, we were assisted by Marie and Jean-Luc. Thank you both for ensuring that everything was going fine.
Coming in on Saturday flood.
Yes, we had to come on a boat, almost. So we'll have another hangout in 2 weeks' time, most probably live from Stanford University. So, and we'll be, in this way, able to answer with, other experts, your questions about the whole course. So that should be another opportunity to meet and to answer your questions live. We have not answered all the questions, so we'll try over the weekend at the beginning of next week to also answer in the written form some of the questions that we could not, we didn't have time to answer during this hangout. So I hope you're enjoying the course, and I can tell you that the next 2 weeks are really exciting physics and astrophysics. So I just hope that you'll enjoy it as much as we do. Okay, bye for now, and see you on the discussion platform, or talk to you on the discussion platform in the coming days. Okay, goodbye.